Okay, so for everyone, we're about to get started with the session. And I want to make sure that the session speaker, our honored guest, is aware that we're about to get started. On that note, it is my great pleasure to introduce our moderator for this session. This is Dr. Tessima. Dr. Tessima is a program officer at the National Science Foundation in the Condensed Matter Material Science. And he has been a champion of the National Society of Black Physicists. He's been really pivotal in enabling us to get the funding to continue these conferences. And it's with great pleasure, Dr. Tessima.
Thank you very much. We are all champions of the National Science NSBP, National Society of Black Physicists. I have my colleagues here, and I have colleagues who didn't make it as well, Suleiman and Alina, that I tried to introduce this morning. Could you please stand up and show your face? But there are other NSFers as well, so it's NSBP definitely has a broad support. So it is my pleasure to actually introduce this session. My colleague, Tomasz in particular, I'm not sure he's hearing us. He's hearing us? If he doesn't, I'll tell everything. Yep. Okay.
Yes, I'm hearing you.
So Tomasz is currently a program director in the Division of Materials Research. He's program director of the Condensed Matter and Materials Research Program, CMMP, Materials Physics Program. Previously, he comes actually from Poland with a PhD. He was a postdoc in New Mexico, and followed up. No, he became a visiting scientist at New Mexico, and took a postdoc position at Los Alamos, which turned into a permanent position there. From there, back into he joined NSF as a program director. I think it's 2014 or close to that. At NSF, he has taken many responsibilities in addition to his role as a program director of the Condensed Matter Physics Program. He served in the Mathematical and Physical Sciences Directorate Office on detail, and he also took a detail, actually has a keen interest in education and in particular quantum education. So he spent time at the directorate, DUE, right, undergraduate education, 1 year. He's a lead person in the NSF and the federal activity in the field of quantum, the quantum revolution, the unfolding quantum revolution. So Tomasz is a great speaker, and I'm very happy that he's going to entertain us for the next 2 weeks. But more than entertainment, he's going to give us very important information about the program and inspire young people here. Tomasz?
Thank you so much, Tess. I just need a confirmation that you can hear me.
Yes.
Excellent. Let me then start sharing my screen. Can you see the slide? Okay. Excellent. Thank you. Thank you very much. I want to start by saying thank you so much to the organizers of this most excellent and renowned conference for the kind invitation. I love talking about quantum. So it's an art actually to stop me. Please, if I'm talking too long, Tess, unplug something so you can go on with the program. I really appreciate this opportunity. I thought that if we have full hour to talk about quantum, I would make it a mix, just as quantum is a mix of so many different fascinating disciplines, from condensed matter physics to mathematics, computer sciences, engineering, biology, pretty much everything in STEM, in sciences, falls under or serves in one way or another the quantum information science and engineering conglomerate of disciplines. So I thought I will make it also a conglomerate of different things. But before we get there, let me show you a picture from almost 100 years ago. That's 1927. People on this picture that many of them you probably recognize. Albert Einstein sits in the very center. Met in 1927 in Brussels in the Solvay Hotel to discuss quantum physics. This is a group of people who, through collaborative effort, back then, almost 100 years ago, put together a new language of describing nature. And today we are trying to use this language, even though we do not fully understand it. After all these decades of intensive research, we still do not fully understand quantum mechanics. But we are using this language to benefit humanity, to make new things, to solve old problems. And it's amazing that this effort started, well, over 100 years ago, if we count 1905, the year where Einstein published his 5 papers as the beginning. And today we have quantum computers, like a picture of one operated by IBM is shown in the upper right-hand corner. We have fantastic fundamental research. And here at the bottom, you can see a picture of a nanowire on a superconducting background with 2 peaks at the ends that are supposed to correspond to Majorana fermions, an exotic quasi-particle to be used someday in topological quantum computers. So there is history, there is mystery, there is applications, and there's fundamental research that's really booming these days. And the field is, thanks to those foundations, really exploding today. And we will talk about this some more. This picture I'm showing you right now, I will come back to it at the end of my presentation. So I want you to have a look at that picture of this group of people and see if you see something interesting about it. Have a good long look. Do you see something interesting in this picture? We'll come back to it. Now, I wanted to make it a mix that may be interested and appealing to everyone. So we will talk, of course, about science. What is it? Quantum information science engineering, what are the components of it? And I will give you some examples from my field. We'll talk about a few examples of fascinating problems in quantum materials. But we will also mix in discussion of policy and role of government that is well established now through legislation in the area of quantum. We will talk about NSF approach and some specific funding opportunities also available through NSF. We'll talk about education in quantum, a key, really key issue in our ability to continue with this research in the future. And we'll talk about broadening participation in quantum, where quantum information science and engineering is an opportunity to work in an impactful way on broadening participation. So we will cover a lot of territory today. Well, what is quantum information science and engineering? You can think of it as this beautiful rainbow of different disciplines converging together in one common direction. And that is really integration of quantum mechanics with information science, with physics, with biology, with other disciplines that examines the uniquely quantum phenomena to be able to describe the world of the small, of the smallest, the ability to use this theory, quantum theory, for storage, communication of information, quantification, and computing, but also sensing, utilizing the quantum phenomena. Quantum information science and engineering combines all of it. And that unique nature of quantum phenomena, such as superposition and entanglement, does not have classical counterparts. But even though today we do not have a uniform interpretation of quantum mechanics, you may have heard of interpretations that started with Niels Bohr, such as the Copenhagen interpretation, or the more recent one like multiverse interpretation, hidden variables interpretation, and many, many others. We do not have agreement and full understanding of what is the fundamental meaning of measurement in quantum mechanics. And you could multiply those examples, but at the same time, we are able to use that language to found a new technology, to build the very rich landscape of technological applications. That's what's really fascinating about quantum information science engineering, and that also is something different, how it differs from classical physics, for example, where you would hope to have all the fundamentals understood at a given point in time and then push the boundary of research by questioning the paradigm. Here we're still coming back to the original point of quantum mechanics, where the original questions posed by Bohr and Einstein are still unresolved today. Okay, why do we really care? That's a great question. And I think the answer presents itself by, on one hand, an absolutely amazing amount of fundamental research. Just NSF supported 31 Nobel Prize winners in the general area of quantum sciences. But also, you can see those advances in science that are linked to quantum being made every day. Almost every week, there is some great paper coming out with breakthrough new discoveries. But also, you can see that industrial partners step in. In the last 5 to 10 years, the industry was growing exponentially. The number of papers published is also growing exponentially. You can see that by counting abstracts at, say, APS Match meeting. Then you can see that in the lower left side of that slide. Patents that represent translation from laboratory to industrial applications are growing exponentially. This is the number of patents as a function of time. The market today, looking from the industrial perspective, has over 100 companies, and it's also growing. The workforce, I met about a week ago with the CEO of a headhunting company who was providing information about specifically quantum market of jobs. And he told us that today we have about 2,000 job openings that we cannot fill in quantum. That number went up by 70% in the last year. It's expected to go up by an order of magnitude to 20,000 jobs in the next 5 to 10 years. So again, amazing growth on the side of fundamental research, on the side of industry. Obviously, the government is following it very closely, and we'll talk about that later. But that also means there is amazing opportunity for everyone who wants to be involved in quantum. There is a way, there is a niche, there is a hope of making a difference in the world if you join that movement. And actually, when you look at job openings again, you can see that there is no specific need for PhDs only or master degrees only. There is need for everyone, from technicians to bachelors, master degrees, PhDs. Everyone can contribute, and everyone can also benefit from this explosion. So that's why we care. Quantum is big science, so it's very appropriate for this hour because it's asking ambitious big questions. For example, are there fundamental limits? How far we can push entanglement and coherence for quantum states? Are there specific limits in time, distance, or scale? What can we learn from quantum phenomena in nature, naturally occurring phenomena, such as, for example, photosynthesis, but also in engineered quantum systems, say topological insulators? What can we learn about emergent behavior, complexity, quantum classical boundaries, a fascinating topic, and their theoretical foundations? And then finally, how do we galvanize the science engineering community to enable the growth in quantum devices, systems, technologies that surpass classical capabilities? These are all very ambitious questions, very difficult to answer, but definitely worth pursuing. So let's switch to some specific examples of big science in quantum, and we'll talk about materials. Materials build the ability of quantum information science and engineering to deliver things, to deliver operations of a quantum computer, to deliver measurements by a quantum sensor, to deliver transport of information of entangled state over a quantum network. But in order to do this, you need materials. So materials can be seen as the starting point of all the quantum industry, technology, and research. And this example here shows materials for qubits. Qubit is a building block of a quantum computer, such as transistor is a building block of a classical computer. Here, qubit is a building block of a quantum one. And we have a few examples of qubits based on superconducting loops or Josephson junctions. That's one type. Another one is trapped ions. Some people use silicon quantum dots. Diamond vacancies or other types of vacancies can be used as a qubit. And then there is a theory that you can use topological qubits. Now, we have Josephson junctions, we have trapped ions, we have silicon quantum dots, diamond vacancies. We actually have already seen examples of first initial very noisy quantum computers built with those types of qubits. We do not yet have a topological qubit, but a lot of research effort is directed in this direction. And you could ask why? Well, if you look at how the quantum computer operates, it requires you to be able to encode a quantum state and entangle it, and then make sure that it stays alive for a long enough time to perform a measurement. So you have to perform operations on it, like entanglement, and then be able to measure. And it's easy to imagine that if that state can only survive a nanosecond or a millisecond, then it may not be enough, may not be long enough to perform a precision measurement or encode an operation. That means the process called decoherence, which is really a decay of a quantum state, is a primary obstacle for us to enter fully the era of quantum computing. Those states live short and they are noisy, meaning they decohere, they interact with environment. And physicists talk about this in the language of collapse of the wave function. What it really means is the particular state disappears, decays, mixes up with the noise coming from the classical environment. The one type of a qubit that would help us avoid it is a topological qubit, because topological systems have this property of being protected from environment by the environment having to break specific symmetries that are very difficult to break. So topological qubits are self-protected from interactions with environment. They would provide a long-lived state for a very efficient and noise-free future quantum computer. You know what the problem is with topological qubits? They don't exist. Not yet, not yet. Some of you, perhaps sitting in this room right now, maybe one day will discover a way for us to not only generate elements like Majorana fermions that could be entangled through a process called braiding and then used as topological qubits, but maybe you'll be able to build, based on that, a fully operational quantum computer and change the world forever. I strongly believe that exactly is what will happen. Now, if you look at the history again of the timeline of quantum science, we have to go back to 1905, 1930. From the first papers to 1930 was a time frame where von Neumann published the first textbook of quantum mechanics. That's where it all started. And from this, we can see one arrow pointing to band theory. There was a way to calculate the band structure of condensed systems, like metals, for example, semiconductors, etc., to build, on base of that theory, to be able to build a transistor. The first transistor was 1947. And then, of course, the huge explosion of electronics, progress of integration, meaning we could put more and more and more and more transistors into an integrated circuit. But then we quickly reach the limits of integration that are described by Moore's law, where what we find is that we cannot make the conducting pathway too narrow. If we go below 2 nanometers, then the pathway will burn itself, even with a very small amount of current that goes through it. So there are fundamental limits. There are other limits too, but there are fundamental limits to how many transistors we can put on an integrated circuit. And that is where we have to stop. This area, currently the only one in electronics, where we are integrating more and more transistors into a chip, has come to an end. We are facing the limit of that ability to make progress. Yes, we are thinking about replacing, for example, silicon technology with something else, like diamond technology or nitrate technology or something else. But it seems that this is a fundamental problem that will stop us at some point from further development. So here we have, to the rescue comes the quantum technology, where, for example, in topological systems, we had the first concepts back in 17th century. Then we established the first theoretical predictions of topological phases back in the 80s. Then there was a discovery of time reversal symmetry protected edge states in the late 80s. And today, the field of, say, topological insulators or topological properties, together with emergent states, is also growing very, very rapidly. And that's why, even though we do not have topological qubits yet, it's very likely that one day we will, especially if you get on board. You see, here is this little sign showing a symbol of a highway. This will be the highway that brings us into the future, the second technological explosion that will be not very much different from what the first one provided when the transistor was built. And then we see the explosion of interest and applications of transistors. We can expect similar things to happen with topological insulators, and in a broader context, of course, in quantum. And this is where you are. You are at the entrance to this technological highway. It's about time you get on this highway. So big science of quantum information science engineering requires novel quantum materials. And that is a vast and booming area of research. It starts with theory. Our colleagues, theoreticians, think of new ways, of new principles, of new solutions, of new combinations of physical properties of matter that can be used to build new materials. And they came up with the idea of braiding, where what happens is you take so-called anyons or non-abelian anyons, such as Majorana fermions, and you build a topological qubit out of them through the process called braiding. And without going into details of braiding, we talked about it already. The huge advantage of that process is that it is inherently protected from the harmful interactions with environment. This is the only type of qubit that we have predicted that would be long-lived and protected from decoherence. So a lot of teams across the world work on very, very hard on trying to first generate Majorana fermions, and second, learn how to braid them, how to manipulate them in a way that will allow encoding of information and entanglement, controlled way, so in a way that will lead us to building a topological qubit. And here is one example of work from Princeton, where again, on the superconducting substrate, there is a nanowire, and at the ends of this nanowire, in special conditions, you can observe special peaks in spin resolved measurements that correspond to theoretical predictions of Majorana fermions. This result, according to the authors, is a smoking gun evidence. According to the critics, is not yet good enough, because if you talk about this issue with, say, Tony Leggett, a Nobel Prize winner from some years ago, he would tell you that the proof of the pudding is in the eating. It's not enough, according to Tony, to show the peaks at the ends of the wire. You actually have to braid. You actually have to provide a qubit and perform computation with it to be able to prove its existence. It may sound strange, but actually I think Tony is right. We have initial, not very strong evidence that Majoranas are possible. What we really need is a process that can only be realized while using Majorana fermions through braiding. Isn't that brilliant? I think it is. And that also shows how much is left to be done in this field, how much is left for you to pursue, how much interesting, fascinating problems are out there. Another example of how anyone can find something of interest in quantum is here. You see, in the center of this plot, you see this schematic diagram of a topological quantum computer that has the process called initialization, where you kind of prepare your machine, you program it, so to speak. Then you create the anyons, then you braid them, means you pretty much move one around another, and then you fuse them to get the result through interference. And then readout, which is analog. So initialize and readout are where the quantum processes touch with the analog processes. And in order to achieve that, and again, I want to stress that we do not have that yet. This is a theoretical concept. But in order to get that there, you need to do something that many people think is impossible. You have to put together the brains of computer scientists who will be coding this thing, of mathematicians who are designing the algorithms necessary to perform the coding and the braiding. You need to put them together with engineers who will actually build the device out of the materials provided by condensed matter physicists. And you need those materials platforms that are stable, operational, scalable, provided by chemists and physicists. So the success here depends actually on our ability to work together as a large convergent team of multiple disciplines. That also, I think, is a uniquely fascinating aspect in quantum. All right, since materials in quantum materials are so much fun, let's spend a little more time here. Many of you, if not all of you, heard about graphene. And in recent years, we have the reinvigorized interest in graphene as a quantum material by using twistronics. When you have two sheets of graphene, put one on another, and then we regulate the properties of this material by twist angle, angle of twist between those two sheets of graphene. And it was found out that in this kind of setup with proper gating, you can go from insulating to superconducting by adjusting the twist angle. Now imagine that outside of graphene, we have thousands of two-dimensional materials that can be put together. We can also put together thousands of layers of different materials. And then if you add twist angle to this as a knob to turn the parameters, the possibilities are endless. Possibilities of getting new materials through twist angle are absolutely endless. And isn't that a fascinating topic also to explore? And of course, I always think, when I think twist, I think Chubby Checker and Let's Twist. He was the best. Classical or semi-classical also offers interesting quantum materials. When we're looking at, say, competing magnetic phases in systems that provide ability to control spin, arrange spin, utilize spin in a way that depends on temperature, pressure, chemical composition. And those phases also can be used to encode information and to provide us with very high sensitivity of quantum sensors. All right, let's talk a little bit now about the policy. So we'll switch gears a little bit to those of you interested in all of government approach and in policy aspects of such big enterprises like quantum information science engineering. Back in December of 2018, the National Quantum Initiative Act was established, and that brought to NSF, DOE, and NIST very specific responsibilities. Specifically for NSF, my agency, National Science Foundation, we were tasked with carrying out basic research and education activities in quantum information science engineering, and also in coordination with other agencies in establishing centers for quantum research and education in QISE. The Act describes similar but slightly different responsibilities for DOE and NIST as well. And you have to remember that quantum has this component of fundamental research, has the component of industrial growth and interest in translation to the markets, but also has a very strong component of safety and security through things like cryptography. Quantum cryptography is hugely important for military, for Department of Defense. So are quantum computers that can hopefully in the future help us simulate some, for example, nuclear weapons or nuclear reactors, etc., etc. It is said that the future wars will not be won or lost by bullets, but by bits and qubits. So Department of Defense and the rest of government as well care very much about developments in quantum. So here you have the attention of industry, the attention of academia, and the attention of many government agencies. And there are specific policy thrusts in terms of national quantum information science policy. First, it's based on a science-first approach. What does it mean, science-first approach? That means that we are realizing there is a lot of work to be done at the fundamental level. The fundamental research has to continue. We are not as ready to take on, say, a moonshot initiative like Apollo program, going to the moon. Because back then, in the times of Apollo program, we would mostly be facing engineering challenges. Fundamental research was ready. Engineering challenge was to build a functioning and safe rocket and calculate everything and provide necessary conditions for people to survive the trip. But these were engineering challenges that in principle could have been solved. We knew that. In quantum, many people believe that we are not there yet. And hence the science-first approach saying, let's focus on fundamentals first and do translation in parallel. As much as we can, translate to industry, but do not forget we need to build up on fundamental research first. Second point is to build a quantum-capable, diverse workforce. Well, as in many other areas of STEM, also here, perhaps even more acutely, we are missing workforce. As I said, 2,000 jobs open today that we cannot fill. We have a need for US citizens because of the clearance process in the Department of Defense area. We have a need in places like Silicon Valley or in general in California for postdocs in quantum, and it's impossible to find one today. There is no postdocs. They are immediately hired by industry. So in academia, hiring a postdoc in quantum is impossible today. etc., etc. And that problem, I always like to think of problems as possible solutions. You see, when it comes to areas of minority serving institutions, historically Black colleges and universities, this is a fantastic, vast area of underserved, underfunded, underutilized too, and very, very smart people who can make a difference when it comes to, say, contributing to quantum workforce. And I think that process of turning a problem into a solution here is obvious. We need to help generate quantum workforce in all those places where we have people, US citizens, that are currently not involved. Seed the interest, seed the growth, help nurture and see how it blooms when all those places currently under involved in quantum can reach the level of productivity, which they without doubt can, benefiting many. So that's number two. Number three, nurture the nascent quantum industry. The idea here is that because of the high risk nature of the quantum information science engineering, industry needs guidance, help, and coordination in their activities when it comes to translation. And government has an ambition to help with that. Providing key infrastructure here, it's mostly about research infrastructure, such as, say, synchrotron facilities, high magnetic field labs, perhaps some other fabrication facilities, nanofabrication, robotic lines for putting together hybrid structures out of two-dimensional materials, etc., etc. And NSF and Tess can tell you much, much more about this as an expert in science infrastructure. NSF is heavily involved in helping in this area. Then the balance of economic and national security, that really boils down to a healthy relationship between the government and private industry, which we know, of course, that academia is all about curiosity-driven research. Industrial partners are all about making money. And the government, of course, has a specific role that also has to do with national security. And balancing that many-body problem is not trivial. And then, of course, international cooperation can be a source of inspiration, exchange of ideas, and growth when done right. It can be risky when not done right. And that's why there is this policy thrust. If you look at quantum.gov, something worth looking at, you will find a lot of information about this all-of-government approach to quantum, including several reports. If you like reading reports, then you will find those reports there. There is several that I would point out. One on quantum frontiers, a recent one on quantum networking strategy, and published earlier this year on workforce development strategy. And then there is one on quantum sensing. But workforce development may be the most interesting one here, because it really describes in a comprehensive way how we need to train quantum workforce all the way from K-12 to PhD. And there is no shortcuts there. We have to start early. NSF was pursuing quantum for many, many decades, but in recent years, we kind of focused through something called Quantum Leap, an all of NSF approach to leading the next quantum revolution. And really, it was an approach that put together representatives, program directors from very, very different divisions across NSF to look at quantum mechanics in terms of how can we enable breakthrough discoveries, how can we observe, manipulate states, how can we develop next generation technologies. And that Quantum Leap, which we pursue through convergence of disciplines, collaboration with partners, and community building, is the NSF approach, where, for example, looking at the quantum workforce, here you can see that it is a sum of materials researchers and chemists, engineers, physicists, and mathematicians, computer scientists. We need to be working in a way that provides the new kind of a student, the new kind of graduate that has elements of all these different disciplines being taught in the course of study. And that is happening already in many places across US, but numbers are not there yet. Maybe I'll skip those few slides in the interest of time. I want to mention one program that's called Quantum Leap Challenge Institutes that was instituted by NSF in response to NQI Act that supports relatively large-scale projects driven by cross-disciplinary challenge. Again, the convergent cross-disciplinary nature is at the heart of that idea. And we found 5 of such centers at the level of $125 million over 5 years. Dealing with new qubits, atomic clocks, quantum networks, error correction, education, and center scale approach allows us to get more than the sum of individual parts, of course, in this focused approach to funding. The impact of centers is huge. We touch on a total of about 500 people through involvement of 31 academic institutions, 180 faculty investigators, etc., 210 graduate students through just this one program, Quantum Leap Challenge Institutes. Another example is the QMA's Quantum Foundries, where we have a center, but the key role in this center is played by partners from industry. The center is working on, say, two-dimensional materials and how to interface them with silicon technology. And then every now and then, there is a question, which way to go? Yogi Berra would say that if you have a fork in the road, take it. But in reality, we need to choose. And here, when the foundry, when the center is facing that dilemma, which direction of research to pursue, there is a integrated role of advisory board that's built out of industrial partners who will tell them which way to go to maximize the chance of future translation. And we see the beginnings of that. The program started a few years ago with the first center, and a year ago we added another one. So we have 2 foundries today. Total budget of that is about $46 million over 6 years. The transformational advances in quantum systems, also known as TACS or TACOS, is a program that, again, looks at interdisciplinary research for new ideas, new concepts, new technologies with focus on quantum functionality. And we had several competitions of that program. I think it's fair to say that we may expect more. The total number of awards was 23 in the first one, 19, and then 10. The total budget so far was about close to $70 million. Quantum workforce, of course, is a huge topic for us. Through activities like triplets, I think I will talk about them briefly later if time permits. An interest in education explored through Q12 education partnerships that comes from K12, of course. And then dear colleague letters, such as the one on advancing quantum education and workforce development. These are examples of programs developed in just in the last few years to advance quantum workforce. One of the new programs that may be of interest to you is Expand QISC. That's intentional and deliberative to really increase participation, capacity building, and critical mass of research and education in those places, those institutions that are currently not involved in quantum or involved at the very early nascent stage. And we have 2 tracks in Expand QISC. One is for individual PIs at the level of $800,000 per award for a duration of up to 3 years. And track 2 is for small to medium scale teams with a budget of $5 million over 5 years. They pursue specific focus area of research, quantum fundamentals, looking at the coherence, at the complexity theory, at the nature of many-body states, etc. Very, very fundamental research. Then the next one is a transitional focus area between fundamentals and simple applications, like in metrology, in control, utilizing superposition of states in a quantum sensor, minimizing noise of a qubit, increasing the resolution of methods to manipulate quantum states. And then the most complex one, heavily relying on application, is focus area 3, where we talk about systems like quantum networks, quantum computing, platforms, test beds, scalability, etc. And then there is focus area 4, which has to do with education and workforce development, such as new curricula, new degree programs, etc. So we couple all the 4 focus areas in one solicitation, Expand KYSE, and we ask reviewers that you might be interested in finding out that. We ask reviewers to look at specifically eligibility of the institution. Is it really a nascent or early effort? How will the effort advance participation of all members of society in quantum? How is it aligned with the focus areas topics? Is it going to increase capacity in this area? We also have an external connection, which is a source of external knowledge, but 70% of funds stay at the original lead institution. And the sustainability, we want to make sure that the plan can continue even beyond the award duration. We recently made 11 awards, 8 in track 1 and 3 in track 2. Here is the list. I will not go into details, but you can see that many of those institutions are 2 institutions. We have HBCUs, we have Hispanic serving institutions. We also have a bachelor's college. So we are very, very looking forward to the results of capacity building in all those schools where the effort in quantum is early or primarily non-existent. And when you think again about quantum workforce education and broadening participation, these topics are very closely coupled through the things that we need to do to build a quantum smart workforce. First, we need to build quantum intuition. For those of you who are older, like myself and Tess, it's too late. Let's face it, Tess, we will never get quantum mechanics. We'll never understand it. It's too late for us. But kids, younger people, they can still get it because they are surrounding themselves to more and more degree, larger degree with the language of quantum, with the first quantum games that you can now download on your phone, with the intuitive understanding of qubits, of entanglement, of decoherence. We were surrounded when we were growing up by classical technology. When you're surrounded by quantum technology, you may develop this intuition. And if you think about it, at the same time, when we cannot really understand the foundations of quantum mechanics, we need to be able to develop this intuition to reduce the barrier of fear. There is such a thing like a fear of quantum mechanics. And all the things that Feynman, Schrödinger, and Einstein said about it increased this barrier. But what we need to do is decrease it. Make sure that folks understand you can benefit from quantum mechanics, even though the brightest minds on the planet still do not understand it. That's not a problem anymore, if you think about it this way. Lowering the barriers, very, very important. The industry-academia partnerships, we talk about it a little bit, but it really leads to efficiency, and both in achieving the goals of industry and academia and also reducing the taxpayer cost. Efficiency is very important. Enhancing curricula. We will never get the workforce if we do not teach quantum mechanics, if we do not teach physics, if we do not teach mathematics, if we remove content from curricula across K-12, across the nation. That has to stop. It's a very difficult problem, as you know, that involves boards of education, that involves broadening participation to a large scale, and where inclusion is an opportunity that we perhaps not fully exploring yet. Interdisciplinary programs, we talked about this, of course. The very nature of KYC is interdisciplinary. And then a good estimation of actual needs. There are people out there who claim that we may be facing a quantum winter one day. Today, nothing shows that it's possible. All the numbers in all the indexes are growing exponentially, but it's not impossible that at some point in the future, some kind of cool down period comes, as it usually does in all areas of technology. We need to be able to estimate and track those. And then, of course, government programs to enhance workforce will provide leverage when we can be supportive of the generation goals, workforce generation goals. That requires a very, very broad look at that encompasses teachers, undergraduate students, workforce development, graduate students, K-12 education, informal education, broadening participation, inclusion, diversity, and partnership. And again, that is something that across NSF, we are actually uniquely positioned to deliver, because we have this place called, it used to be called EHR. I forgot what it's called now. They recently changed the name, but it's a composition of divisions that have to do professionally with establishing, managing, developing, and maintaining and managing programs in education, in broadening participation, diversity, and inclusion. Of course, in NSF, we have divisions that are fundamental research oriented from the beginning, such as across MPS, we have physics, material sciences, astronomy, mathematics, and chemistry. We have Directorate of Computer Sciences, we have engineering, we have biology, etc. But we also have this part that has to do specifically with education and broadening participation. And I think if we find a way to effectively unite the interests and the collaborative platforms for people coming from all these divisions, NSF can fully participate in this together. Fire on all cylinders, so to speak. I see that my time is running out. I probably talked too much, so I will skip a few slides and I will go back to what I promised you. Initially, we will zoom in on this slide that I showed you as a first slide again. But first, a bit of a reality check. When we talk about broadening participation, we rely on reports produced by National Science Board. National Science Board is a governing structure for NSF. And it's absolutely outstanding job of National Science Board has to be mentioned when it comes to producing reports. However, I have to warn you, if those reports, you will like reading those reports probably on Halloween, or if you like scary movies, because these reports are scary. They do not sugarcoat. What they tell us is that the relative change, for example, in percent of women in science and engineering occupations almost didn't change. There is a very small change between 1993 and 17. The salary difference is 29% between men and women for bachelor and 21% in PhD. Salary difference between white employees and employees of other races is 21% for bachelor and 12% for PhD. So what does it all mean? The way I read this is that we are not doing a very good job as a government in broadening participation. We are not meeting the goals of diversity and inclusion. And we should think about this complex problem, perhaps through the lens of quantum information science and engineering as an opportunity, and change the way we do things. Obviously, if we do more and more of the same, we cannot count on a different outcome. So these data from NSB, reliable data, do not lie, and they paint a bleak picture. And then I promised you that we'll come back to this. So you may have noticed in this picture, we have 28 men and only one woman. Marie Curie Skłodowska, she's in the front row, third from the left. By the way, she got 2 Nobel Prizes, not just one. But at that time, if you count the diversity in this picture, you will end up with 3.46% diversity. 1 woman, 28 men. If you look at Nobel Prizes in physics between 1901, when there was the first Nobel Prize, and 1931, so the first 30 years of Nobel Prizes, you will find 35 men and 1 woman. That's 2.8% diversity. So now let's move on 100 years forward to the last 30 years. And sure, after all these decades of intensive work on improving diversity, on broadening participation, we made some progress, right? Wrong. If you look at the last 30 years in Nobel Prizes, we look at 76 men and 2 women, 2.6%. We went down from 3.6 to 2.6 in the last 100 years. Another prestigious prize is Wolf Prize in physics in the last 30 years, 40 men and 1 woman, 2.5%. That leads me to this question, and I will maybe leave you with that question. When it comes to broadening participation in quantum, do we need evolution or revolution? Should we continue doing what we're doing, evolving slowly, using the same approaches, or should we rather have a dramatic, impactful change? I leave you with this question, but just to summarize what we talked about, we looked at quantum as a big science. We looked at examples of big science in quantum materials. We discussed briefly the role of policy and the role of government, NSF approach, the importance of quantum education. We kind of skipped a little bit of slides on that in the interest of time. And then we looked at this broadening participation as a vast opportunity, especially for quantum information science and engineering. Well, thank you very much for your attention. And I don't know how much time we have for questions, but I'll be certainly happy to answer.
So if we could thank our speaker. Dr. Tomasz, thank you so much.
Thank you.
We do have some time for questions. And if anyone has a question, if you raise your hand, we have a couple of folks that'll bring microphones over. We have one over here in the front row.
This is an online question. What effect do you expect quantum mechanics could have on space missions and stations?
Excellent question. We know that space exploration is something that captures our imagination, right? It's a brilliant frontier of science, of research and technology. And so is quantum. So it's not surprising that the two converge. NASA is actually part of the broad government group of agencies involved in quantum. And they are primarily interested at NASA in being able to sense and detect things at the very, very smallest possible level of signal. Sense and detect, such as magnetic fields of Earth, but also of moons and planets, but also detect individual photons coming from the edges of known universe. And of course, applications of quantum mechanics are countless when it comes to sensing. They're also interested, of course, in future quantum computers to be able to calculate what's happening inside a star. And yes, the short answer is yes, there is very, very much of the interest and overlap.
Thank you so much. Next question.
Hi, thank you very much for this talk highlighting this very hot area of physics right now. I am here from the University of Maryland, and I'm wondering if you, I'm going a little bit out on a limb because I know you're not NSA funded, but do you know about the Laboratory for Physical Sciences at University of Maryland?
Yeah, I know Chris Richardson and many, many others there. Yes.
Yeah. So would you mind if I gave a 20-second pitch on a coherent program that wants to support these efforts?
Oh, I don't mind.
Yes. So the Laboratory for Physical Sciences and UMD, University of Maryland, are partnering for a fellowship program called Pathway to Physics PhD, which is a fully funded scholarship program that will bring scholars to the Laboratory for Physical Sciences to work on these sorts of problems and opportunities before they even get into a UMD classroom. Right now, we're accepting applications on a rolling basis, and we're going to select our second cohort of hopefully many in the next few months for next fall. And if you're a sophomore or a junior, just keep in mind that we'll be looking for applications in October and November in the coming years. Thanks a lot. I also have a table at the exhibit room.
Thank you. There's a question over here.
Yes, I have been following NSF and their programs for a while, and they seem very reluctant to go to the K-12 stage, which it seems like that's where the answer is. As you pointed out, there's been programs for a while now and hasn't had much success. And I think it's because they start too late. Many programs want to wait till undergraduate. Most programs like the NSF RU programs, they usually want juniors. Usually you're losing people in the freshman year. And you're losing them in the freshman year because they're not prepared in the lower levels. They're not thinking in the way that they need to be thinking until they hit 12th grade physics, where they are now trying to get them to correct the way that they've been thinking for 16 years. And so no surprise, that hasn't been successful. But NSF doesn't seem to want to change their strategy. Is it changing now?
And what a wonderful question, insightful question. I have to answer it honestly, right? Because honestly is where the conversation has to start. And in my honest opinion, you're absolutely right. We have a way of doing things that sometimes is difficult to change. And one example is that we, especially in this area, when it comes to, say, education, broadening participation research, diversity research, we tend to focus on funding the research, the epistemology generation, the writing of papers. And it's all excellent, excellent knowledge, well done, professionally executed, and true. The problems start when it comes to implementation. We can fund 150 awards in K-12 curriculum generation in STEM. And we do that. But who is going to stop teachers from leaving the professions? Who is going to fix the crisis that we have right now? And in some states like California, in Los Angeles County, teachers are being subsidized because they cannot afford rent. Who is going to negotiate with state boards of education and local boards of education in every county that what contents of curriculum should be improved? These are very, very difficult problems to solve. And these are the problems where we're not making a lot of effort. We are very, very comfortable in funding research side, in generating epistemology. We do not have good answers when it comes to translation and implementation. That's a huge problem for us. I think that needs to change. We need to look into that. And a good example is we have a number of programs here listed on this slide that work with K-12, with undergraduates, with opportunities for graduates, etc. We have 126 right now programs across NSF that you can apply for funding that is related to broadening participation one way or another, 126. But we are not making a lot of difference. The needle is not moving. So we have to sit down and think how to change that. That conversation is starting, right? I can tell you when I joined NSF 8.5 years ago, we didn't talk about it at all. Now we're beginning to talk about it. So in some years, I hope there will be change. There must be change. And voices like yours are critical and very important in making sure that change happens.
Thank you. Any other questions? Yes, there's some online questions. Thank you, Jessica.
So this is from Carlton Smith. How eager is the NSF in funding possible quantum effects in biological systems, photosynthesis, and I'm gonna mess this word up, magnetoreception, etc.?
I can tell you, I'm very eager. I see that fascinating flow of papers that talk about quantum aspects of photosynthesis. And in more recently, I think about 2 weeks ago, there was a paper about possible quantum entanglement explaining some specific MRI results in human brain. These are fascinating topics. Also, they are very, very high risk because we are accustomed to thinking of quantum states as decohering so quickly that in a conditions of something wet and mushy like our brain, it's impossible, and room temperature or higher than room temperature, it's impossible to have a stable quantum state, not to mention entanglement or superposition. So we have to find out, how is this possible? We have breakthroughs on the side of biology, but we also beginning to see some breakthroughs on, say, condensed matter physics, where we have the first examples of room temperature superconductivity under pressure, right? So a very, very, very much quantum state pertains all the way up to room temperature. And then, of course, there is a level of complexity in bio that does not exist elsewhere. All the possible scales conspire against us to be able to understand them. And that is a challenge, a fascinating challenge. So yes, I'm very much for it. I believe in the future calls. We were open to bio already in the past. I don't think bio made a huge dent in terms of number of proposals funded, but I believe in the future calls, this percentage or success rate will grow.
Thank you.
Two more online. Do you think quantum mechanics concept in science fiction help or hurt interest in quantum computing? And then the next question, because I think they're easy to remember. If you were an undergraduate again, would you focus more on a mathematics or physics path for future in quantum science?
Oh my goodness, what wonderful questions. First of all, I love science fiction. Isaac Asimov, Stanisław Lem, Strugatsky brothers, many others. I couldn't stop reading those books when I was a kid. And definitely that poisoned my brain when it comes to think about technology and science and research in general. You have to dream. We have to dream. And dreaming is the dreamy visions of the future is what got me interested in fundamental research. So coming back to the second question, my choices of what to do after high school were dictated to some extent by my interests, and I was interested in mathematics, in physics, in geology too, but to much larger extent by love. I fell in love with a girl who decided to study mathematics in my hometown. So I decided to study physics in my hometown, and then we got married, and that happened 32 years ago. We're still married today. So it's like this. If you have a dream, if you love doing something and you do it and you get better at it, universe will take care of you. Let the universe take care of you. Just find your passion. It's a much more important question whether I should study physics or chemistry or something else. The much more important question is, what is my passion? What do I love to do? Find that.
Thank you very much. I think we have one more question.
Okay, awesome. So I really want to harken back to the discussion around K to 12, learning about K to 12 quantum computing and everything versus undergraduate, because I work for a charter management nonprofit, specifically in education and policy. And I was wondering, do you think that the issue is more or less with the education policy in general before entering college, or do you think the issue is more in the undergraduate, graduate level?
They are different issues. So when it comes to undergraduate and graduate levels, we are not producing quantum engineers or people who are set up for success in quantum information science engineering. We're producing physicists, chemists, mathematicians, computer scientists. What we need to be producing is someone who has a little bit of all of these areas. And there are some initial efforts across the nation, Maryland, Chicago, Santa Barbara, some other places where this kind of approach to undergraduate, especially graduate education, is being implemented. And on the K-12 side, it's a very, very different problem. It has to do with, first of all, the need to develop a new baseline for curriculum. And I'm showing on this slide one of the first attempts that we had back in early 2020. We get together academics, teachers, high school teachers, and industrial types to end up with a list of 9 key concepts for QIS learners. That's in K-12 sphere. So here is the 9 key concepts. You can find more if you Google Q12 education or Q2 work. You will find description of those and a huge number of free educational materials for curriculum building and execution of teaching in those 9 concepts. That was the first step. We quickly realized that implementation of that step requires a lot of work on the side of teachers who on one hand are underpaid, undervalued, on the other hand, facing a lot of red tape when it comes to implementation of changes in curricula. K-12 is a very difficult field to implement change. It doesn't mean we should stop. No, we need to find a way to do that, because without this lake in the mountains, it doesn't matter how big of a pipeline we build. The lake is dry. Nothing will flow. And we have to fix the K-12 problem before we can dream about future workforce in quantum.
Thank you so much. We have time for a couple more questions. Is there another question? Okay.
Hello.
Yep. Hey.
We had talked a bit on this topic of K-12 and bringing people into physics and quantum. I guess it had been mentioned at some point in this conversation that the curriculum itself has cut back insofar as like especially science and mathematics. And from personal experience, like my younger siblings all go to school in the state of Indiana, and at least in middle school, elementary school, they've switched to doing like one science class a month or once a week instead of like consistently doing classes. And that goes down, I guess, to the way the schools are run themselves. So I guess my question stemming off of that, we've talked a lot about how, I guess, the teachers and like how the teachers are treated and how teachers are paid affects how students are taught. But I guess I'm wondering if it would be smarter to start with that aspect, or I guess an administrational aspect, and going, you guys using the NSF's power to, with the government itself or whatever state governments, to change the schooling system in and of itself, the curriculum in and of itself. Does it start with changing the curriculum, I guess, or does it start with changing the teachers, or not, that you know what I mean?
Oh, excellent questions again. What a fantastic audience this is. Yes, I agree that's a problem. I think I was clear about that. It's a huge problem and a difficult one. I do not think NSF can do everything here. NSF by itself can change away from epistemology generation to implementation by pointing what needs to be done and how. But we have no power in terms of telling, say, a local school board in Boulder, Colorado, what to do. By the way, this is a place where they're doing actually an outstanding job. But we have no power in telling the Federal Department of Education what to do. We can, however, now through NQI, and we're doing that, coordinate the efforts and put constant pressure. And that's one of those reports that was specifically on the national posture, federal posture on quantum education, is doing that. We are pointing out those inadequacies, and we're making sure that they are communicated to all parts of federal government. But that requires more than just federal government. Also, things like salaries for teachers, that in many cases, teachers have to take more than one job just to survive. That shouldn't, obviously, it should not be like that. Again, in Los Angeles County, there are two categories of citizens of the county who are subsidized for rent. One, people with mental illnesses. Two, teachers. That shouldn't be like that. If teachers are leaving the profession, then who is going to generate future workforce in a critical area of strategic importance for the nation? We have to do a better job as a government in trying to propose solutions for that and support those solutions. And I believe that the sphere of minority serving institutions, historically Black colleges and universities, this is where we should be looking at for solutions and for help. But we cannot just demand. We have to provide, we have to fund, we have to appreciate and build critical mass and capacity locally to turn this problem into a solution.
Thank you so much. I actually have one question before we get to some housekeeping items. I noticed you put up that we've sort of fallen behind in terms of women receiving Nobel Prizes, and you put up some details. I love the picture with Madame Curie and Einstein and all the rest. I'm just wondering, in quantum and in these other fields, so going to the other extreme, so we have the K through 12 issue of just getting people into the pipeline by the time they get to be an undergrad. But on the other extreme, I think the fact that we've gone from 3.6 down to 2.6, and that is nowhere near 50%. Could you just speak a little bit and tell us maybe what are you seeing as a program manager at the National Science Foundation? What are you seeing as far as grants and recipients and programs that support women and just the number of papers being published? Because those are some staggering statistics and all in the wrong direction, I should add.
Yes, I fully agree. I fully agree. I think the problem is that we have learned through research how to identify those problems, how to identify, for example, reasons why girls in K-12 leave mathematics. We now understand this process quite well. We have never identified effective, impactful mechanisms to counteract it, to reverse that. In quantum information science engineering, on average, we have 7% of women. That's much, much worse than in many STEM disciplines. The issue is not improving. We clearly have to do a lot, and at the same time, I think we are just not ready for two reasons. Why? First, the inability to move the needle, as I discussed before, comes from the fact that we're very good at epistemology and very bad at implementation. And two, there is also an inherent problem associated with not fully understanding and not sharing this vision of importance of diversity, integrity, and broadening participation, and inclusion and broadening participation. I think that from my perspective, and I'm not saying that now on behalf of NSF, it's my personal view, I think we need to do a lot to change our own hearts first, change ourselves first, go through this internal change of us before we start telling the world how to change. And I have no indication that this process is happening. But we have to be patient, maybe. As I said, 8 years ago, I didn't hear this discussion. Now I'm hearing it, and it's growing. At some point, we may even arrive to a conclusion that we need to change the way we do broader impacts. Think about it. We have small programs with specific funding that we know is not enough to help, say, MSIs. At the same time, we have over $8 billion going out the door every year in form of funded proposals, where every one of these proposals contains a broader impacts element. Are we doing a good job using this massive stream of funding? Are we doing a good job in making sure broader impacts are really impactful and not just a way to mark the box and get your project funded? I think these are the simple questions that have very complex answers that we need to start looking for very quickly to make impact.
Thank you so much, Dr. Thomas. If we could thank our speaker again.
My pleasure. Thank you so much for your kind invitation.
This has been a wonderful Big Science Hour. We do have some housekeeping. Dr. Jessica Harris is going to come up and say a few words.
Thank you, Dr. Tomasz. Good to see you. Thank you so much for speaking. So thank y'all for joining. I see y'all are getting our notifications, which is great. How many of y'all have downloaded the app? No shaming. Yay. So you're getting my notifications. So we're all going to head where now? Need a little bit more enthusiasm. We're heading where now? Yes, Omni. So for our students in the room tonight, dinner is on your own, but you can pick up the gift cards the same places you checked in at. So you will see Monique Howard to pick up your gift cards between 4:30 and 6 o'clock. So 4:30, 6 o'clock. Don't worry, if you walk out, you'll forget. I am sending notifications to you, but please make sure you pick up your gift cards for dinner tonight from 4:30 to 6 o'clock, the same place you had check-in from Monique. Thank you. We're all heading where now? Okay.
Thank you.
Jessica.
All peace, take it to the land.